everyone, in today's video we're going to talk about the intermediate value theorem. We did an investigation with this in class and I think the idea is pretty intuitive, but I want to give you an idea of what these problems are actually going to look like when it comes time for our exam and the AP exam. And this is usually a bit tricky, so I think it's going to help here if we work with a specific function. So the first thing I want to do is I'm going to use this function f of x equals x minus 2 quantity squared plus 1. So hopefully we all recognize that as a parabola that's been shifted to the right 2 and up 1. So I want to make just a really basic graph here. And I'm just going to work kind of in the first quadrant here. So let's see, 2, 3, 4. So let's see, if I'm working starting with f of 0. I've got 0 minus 2 is a negative 2, quantity squared is 4, plus 1 gives me a positive 5. And I'm just going to plot in some more points to kind of get our shape here. So 1 minus 2 is a negative 1, squared is positive 1, plus 1 is 2. If I plug in 2, that's going to give me 0 plus 1 is 1. And again, that makes sense for that vertex to be at 2, 1, because we said it was shifted right 2 and up 1. And then I know this is going to be symmetric, about x equals 2. So I've got this. So this is the function we're going to kind of use in the graph to discuss this intermediate value theorem. And I'm hoping if we have kind of a concrete function to work with, it might make this a little easier to understand. So here's the idea. In order to be able to use the intermediate value theorem, we have a couple of conditions that have to be true. The first one is that f of x has to be continuous over a defined interval. So we have over the closed interval from a to b. So let's say in our example, we're going to talk about the interval from 1 to 4. Again, those are the x values. So this is our a and this is our b. So we're really talking about from here to here. Okay, so now our function is obviously continuous over that interval. There's no asymptotes, holes, anything like that. Now, the second condition is that m is some number between f of a and f of b. So let's take a look at what that means. In our case, let's say we called this a and this was b. In our case, I know that f of a is equal to 2. That's the function value at when x is 1. In this case, our b is when x is 4. Our function value there is 5. So now it says m must be some number between f of a and f of b. So I'm going to choose m. Let's just say it's 3 right here. Okay, so I have my two conditions. I know my function is continuous over the interval, and I know this value n is essentially in between the function values at the endpoints of the interval. Now, here's what the intermediate value theorem tells us. It says if those two conditions are true, then we can guarantee that there exists a number c in between a and b such that f of c equals m. And I feel like here is where, let's make that capital so it's the same value. Here's where people get a little lost in kind of the language of this thing. All we're saying is that if my function is continuous and this value m is in between the function values at the endpoints, then the function essentially has to take on this value m, and here I can see it actually takes it on here and here, but it has to take it on at some point in that interval. In this case, at this value here. Now, this theorem doesn't tell us where that happens, it just guarantees that somewhere in between our defined interval, our function is going to take on that value. Now, if you're still feeling lost, that's okay. Kind of hang in there. I'm sure we'll have to have a lot of discussions around this, but let's look at some problems now. Again, the big idea is that we're just guaranteeing that our function takes on a given value somewhere in between the interval that we're looking at. All right, so let's take a look at a problem. Our first problem says, suppose, this should say f of x, equals 25 minus x squared. Now we know that's a parabola that's facing down, so we know that's a continuous function. And I'm just going to make a note because that's our first condition. If our function isn't even continuous, then we can't use the intermediate value theorem. So the question is, can you guarantee a value c on the interval? Here's that interval we were talking about, from -2 to 8, can we guarantee there's a value in that interval such that the function value is 0? So here's what it's going to look like. We already know it's continuous. The next thing I have to check, which is this bullet point here, is that this number, this is that m we were talking about, we have to check if this value is in between f of -2 and f of 8. If that value isn't in between these two values, then the intermediate value theorem doesn't apply. So let's go ahead and do this. Here I have 25 minus a -2 quantity squared. This is going to give me a positive 4, so 25 minus 4 is 21. See, f of 8, I have 25 minus 8 squared. So I have 25 minus 64. Let's see, what is that? I've got to work that out here. Yeah, it's going to be 29, negative 29 if I didn't mess that up there. All right, so now I go back and check. Is 0 in between these two numbers? Since it is, now I can, by the intermediate value theorem, guarantee that there's some value in this interval that has a function value of 0. So here's what we would say. We would say, since f of x is continuous, that was our first condition, and we know that 0 is in between f of 8 and f of -2. Right, we've met our first two conditions. Then, by the intermediate value theorem, and we just abbreviate that IVT, there exists a value c in that interval such that f of c equals 0. And again, this is what we call an existence theorem. It doesn't tell us what this value of c is, it just says that it exists. All right, let's take a look at another one. So here we have, again, the same function, which is good because we already know that this is continuous. Okay, and now we have a different interval, and we're wondering if there's a value c in that interval that has a function value of -3. So again, we need to check the function values at those endpoints. So we're going to check f of 2, and we're going to check f of 5. So I have 25 minus 2 squared. It's going to give me 21 again. Now I have 25 minus, let's see, 5 squared, which is going to give us 0. And so here I actually notice a problem. this function value is not in between 0 and 21. So I actually cannot use the intermediate value theorem to guarantee that this exists. It doesn't mean that it doesn't exist, it just means that the theorem can't guarantee it. So I would say, since -3 is not between f of 5 and f of 2, IVT does not apply. Right? So in other words, we cannot guarantee a value C in that interval such that f of C equals 0. Now, the biggest complaint we get about these types of problems is that people don't like writing out these explanations. And I will tell you, it's going to be important that you memorize the conditions and the conclusion and how to write these statements, because you don't want to be losing points because you haven't memorized that structure. All right, so these are kind of like the basic level problems, just having a function and a value and determining whether or not you can use IVT to guarantee that value exists. As we flip the page here, these questions are going to look more like an AP type question. So let's see what that would look like. Here it says, consider the function f of x equals x cubed plus 1 on the closed interval 1 to 3. All right, so according to the intermediate value theorem, there exists some number c in the interval, open interval from 1 to 3, such that f of c equals what value? So here we have to think about our conditions. We already know that this function was continuous, so that's why we can even use the intermediate value theorem. Now remember, our second condition said that this value, the one we're trying to find here, had to be in between the function values at the endpoints. So IVT is only going to guarantee a value that's in between these two function values. So let's go ahead and calculate that. F of 1 is going to be 1 cubed plus 1, which is going to give us 2. And f of 3, let's see, is 3 cubed plus 1, which is 28. So IVT is only going to guarantee me a value in between these two function values. So if I look at my choices, 0 is not in between those two, nor is 1. 3.56 looks like a good option. It is in between. And if I look at D, 1.79 is not in between either, so I know it has to be C, because that's the only value that fits that condition of the intermediate value theorem. All right, let's look at number 4. 4 says to consider the continuous function f of x in the table below, so we've got some function values in our table. It says if the intermediate value theorem can be applied on this interval, which means it must be continuous over this interval, what is the minimum number of zeros for the function on the interval? So what's the minimum number of times that f of x has to be 0? Now, I know it's going to be 0 at least when my function values change sign from negative to positive or positive to negative. In other words, I can't go from -2 to 1 without crossing 0 if I'm continuous. So this is going to be one time I at least know I have to have a 0. So if I look here, again, to go from 1 to -2, I have to cross 0. Now, I don't really know what's happening in between 0 and 2. It's possible that I've crossed the x-axis more than once, but I can't guarantee that. So looking here by these sign changes, I can only guarantee that I have a minimum of 2 zeros based on that data. All right, last problem here. So 5 says, let f be a continuous function such that f of 2 equals 5 and f of 5 equals 2. Okay, then it says, let h of x equal f of x minus x, and explain why there must be a value r on the interval from 2 to 5 such that h of r equals 0. Now, one of the things that we're going to have to learn, when they're asking us to guarantee that a function takes on a specific value, that's when we need to use IVT. Okay, so IVT comes into a place when you are asked to guarantee that a function takes on a particular value. So when they're saying it must be a value, I know that's IVT. So let's think about our conditions. Now we're looking at h, this function h. And my question is whether it's continuous. So here I have a difference of two functions. My first function is f, which they tell us is continuous. I know the function x, that's just a linear function, is continuous. Since the difference of two continuous functions is continuous, I know that h is continuous. So far, so good. Now, I also know that I have to take my function h and I have to evaluate it at the endpoints of this interval. So I need to determine what h of 2 is and h of 5. And I know I can only guarantee this value exists if 0 is in between these two function values. So h of 2, if I'm looking at my definition here, h of 2 is going to be f of 2 minus 2. Well, they give us the value for f of 2. That's 5 minus 2 gives us 3. h of 5 is going to be f of 5 minus 5. f of 5 is 2 minus 5 equals a negative 3. And so now I know that 0 is in between here, so we actually can guarantee that value. So again, when we're writing our justification here, or explanation, we first have to state the conditions. So we would say, since h of x is continuous, that's our first piece. So maybe I'll kind of underline the pieces. The first statement is that the function's continuous. Then we have to say, and this value is in between our function values here. So h of 5 is less than 0, which is less than h of 2. That was our second condition. Now we can put our conclusion. By IVT, there exists a value r, and you can see I'm kind of taking this from the problem. There exists a value r in this interval such that h of r equals 0. Okay, I know that was a lot, and there's kind of a lot going on here. I'm sorry I can't be with you in class today, but I'm going to ask that you kind of work together, do your best getting through the practice, and then we'll have plenty of time when I'm back in class to go over any questions that I'm guessing you'll have. So thanks for hanging in. I know this was a bit longer of a video. Good luck with the practice, and I'll see you back in class.